Hello and welcome to Mr. Jackson's class. Today we're going to finish up bonding, and we want to finish up the other types of bonds that are available out there. So we're going to talk today about metallic bonds, polar bonds, which are a form of covalent bonds. But before I do that, I really want to go back and clarify a few things. So let's really quick give you the things I want to talk about. We've talked about ionic bonds, which are when electrons are transferred from one element to another, and then they become oppositely charged and they attract. Covalent is when there's a sharing of electrons, okay? And sharing can occur two more ways to hold atoms together to form compounds. And so why do some share? I want to clarify this a little bit even more. But then there's what's called polar covalent, which is called unequal sharing of electrons. And that can happen. They can share, but one will pull on the electrons more than the other. And we'll talk about that as well. And then metallic bonding in metals like iron and tin and lead and all those big famous metals that we use in industry, they actually share their electrons too, but they group share. And this is known, so these electrons are free to move throughout all the atoms as they're close together, and this is called a sea of electrons. And I'm going to try to draw these a little bit to talk about them more in a little bit here. So I want to talk about our metals and nonmetals and explain really quick. We mentioned that there are ionic bonds. When a metal reacts and hooks up to a nonmetal, these love to give away their electrons, and these love to take them because they're so close to becoming a noble gas, and these are close to becoming a noble gas. I mean, if sodium number 11 can lose just one more, it acts like neon. So there's a benefit to just give away your electrons, because then what happens is your lower levels have 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, and now it has one more in this outer shell. So if it can just get rid of that shell, the chlorine, which has 2 electrons on the first shell, but then it also has 8 electrons like sodium does, 1, 2, 3, 4, 5, 6, 7, 8, but it has out here in this third energy level, it has 7 electrons, 1, 2, 3, 4, 5, 6, 7, and so one more would make it perfect like argon. So it would love to take it. So these transfer. Sodium then becomes positive, chlorine is now negative with the extra electron, and then they attract each other and pull together. So that's called an ionic bond because the atoms are actually charged and formed ions. But now, why would things want to share electrons? Well, there are lots and lots of materials, but not as many as the ionic materials, but that are made up of 2 nonmetals, like carbon and oxygen. You've heard of carbon monoxide, carbon dioxide. There's carbon tetrafluoride. There's tons of different kinds of nonmetal materials that are made up of just these kind of atoms over here. So they have to bond differently. Why? Well, let's look at that. Let's put carbon with oxygen. Well, carbon has 4 outer electrons. So we're going to use the Lewis dot structure. Oxygen has 6 outer electrons. Okay? It would like 2 more. So what it does is it goes ahead and it reacts with carbon by sharing the electrons, and so their clouds overlap. So carbon will go and put its orbit or its cloud of electrons, it will let them overlap with the oxygen, and then the oxygen will put 2 electrons in this area, and so will the carbon. And so now the oxygen, because it put 2, it's these 2, and then it has still 2 more that's around it, but now at the speed of light, these shared electrons make it feel like it has 8. And so it actually satisfies that rule where it wants to act like a noble gas. Carbon, however, still has 2 more it would like to share, so what it does is it finds another oxygen, and then this oxygen also shares 2 of its 6, and this carbon, which had 4, puts 2 more here, and now carbon feels like it has 8 moving around it. Because remember, this is moving at the speed of light, so it doesn't know they're gone. So carbon dioxide, which we give off out of our bodies, they make a nice stable compound by sharing electrons by overlapping clouds. Ionic materials do not overlap. They don't need to overlap. Okay? They just transfer electrons away, they gather a charge, and they attract by the charge. But these, they attract each other because they actually touch and overlap their clouds and share electrons. So this is called covalent bonding, where we have cloud overlap and sharing of electrons. And so I wanted to clarify that, and the Lewis-Stock structures help us do that. Okay? So let's move on from there, and let's finish up our ideas. We've talked about bonding and how to actually name them. Mono-di-tri system, that's good. Okay? But we need to finish up our chart. So let's go ahead and pull up our PowerPoint. Okay? Oh, I meant to pull up our table. So let's fill in our table, okay? Let's talk about the last type of major bonding, but really this is just a form of covalent bonding because metals actually share their, so it's actually a type of covalent bonding. And so we know that metallic bonds are created by a metal attaching to a metal. There is 2 metal atoms, just like this one is a non-metal and a non-metal. Okay, how do they do that? They do it by electron sea, or a sea of electrons. And I'm going to draw that here in a little bit so you can visualize it. So that means there's a sea of electrons. And I guess the best way to visualize it would be so we have these metal atoms, and remember, we talked about this earlier, metals would love to give away their electrons, and that's why there's so many that have positive charges. They're givers of electron. So what happens is, they have these atoms, and they're so close and tight together because we know almost all metals are solid. Okay, there is a liquid one, which is mercury, but they get very tightly packed, and their outer shell of electrons, they really want to transfer them away. So what they do is they let those electrons actually go free, and they're running around everywhere in between. And it doesn't make a difference where they are, just as long as one's close by to make them satisfied for their protons and neutrons. So if you put an electron in, it doesn't care if this one's by or that one. It'll push electron out really easily. And that's why metals are great conductors of electricity. They just have all kinds of free floating, or a sea of electrons just moving in between from their outer shells that they've all let go of. Okay? And so they group share. It's kind of like people that go to a park, they have a bunch of children, they all take turns, they kind of all watch the park as a team, and they group share while their kids are playing together. Even teachers do that in playgrounds, okay? They all they look around the playground watching each other as a team, so all the kids are playing, okay? So that's what's going on there. Also at the same time, the most type, we call this kind of structure, is called the electron sea bond formation, metal to metal, okay? And these are called delocalized electrons. Because they're not in one spot. Delocalized electrons. Physical state, they're mostly solids. Okay? The melting point, very high. We know metals are very strong. And so this is a very strong way to bond. Okay? Okay? And are they soluble in water? No. You can put, iron will rust over thousands, hundreds of years, but it takes a lot. So we don't consider that it can dissolve very fast. Is there any kind of electricity? Yes, they can conduct electricity in all forms or all states, any form. They are all conductive, solid, liquid, and gas. Are there any other properties? Sure. They're malleable. They are ductile. This means you can draw them. They can be beaten and shaped. They can be drawn into wires, and they're lustrous, which means a lot of them are shiny. Okay, so those are some qualities of metals, and those kind of bonds are very unique, but they're a type of covalent bond. It's a sharing bond, but a very unique type of sharing bond. Okay, so let's move on. now that we've talked about ionic and covalent, I want to talk about the smallest particle. If I had a sample of table salt, which is NaCl, if I kept cutting it smaller and smaller and smaller, and the last thing I have, there's a name you used to use in elementary and middle school. It's called a molecule, which is the final last little bit of one of each. Well, if it's ionic inside, we don't actually use the term molecule because it doesn't have an overlapping cloud. Only the things that have overlapping clouds, the smallest part is a molecule. Actually, the smallest part of an ionic material is called a formula unit. So if you ever see that word, it really does mean molecule, but they use that to indicate you're talking about something with ionic bonds inside. So it's just like a molecule. Covalent particles, if you cut them down, so if we took water and we took it in smaller and smaller and smaller samples, finally the last thing we have is one H2O. That would be a molecule because it does have overlapping clouds. We have got an oxygen and hydrogens, okay, and so that would be a molecule. So I wanted to make sure I mentioned that. So if you ever see this term, it really means molecule, but it's the molecule of an ionic material. Okay? So we are gone through quite a few things. Now I want to talk about how do we visualize these bonds, and here we have them right here. Let's draw a covalent bond that's not polar. So what do I mean by that? That means we have an atom where we have the nucleus, and we have these atoms that have overlapped the clouds, and the nucleus is in the center, and there's electrons being shared in here, and it's a perfect overlap, and the electrons are moving back and forth equal amount of time on both. That would be considered a pure covalent bond. But there are other bonds that are covalent, but they're not shared equally. This is being shared equally. But we also have unequal sharing. And what is that? What that is we have an atom like water. Let's look at water. It's the best thing. Here we have oxygen. Oxygen has, remember, 6 outer electrons, and hydrogen has only 1. And hydrogen would like to be like helium and have 2 electrons, so it shares with oxygen, okay? So the hydrogens overlap their clouds, but the hydrogens are such small atoms that when they put their electron in to share, and the oxygen has its other 4, so it feels like it has 8, 2, 4, 6, 8, and then the hydrogens feel like they have 2 like the helium, they're happy. But the oxygen is kind of not very fair. It likes to pull the electrons more onto itself because it has a higher electronegativity. It's a word we'll talk about here in a minute. So some atoms are kind of unfair how they share. So if the electrons are over here, this partial, and this little S with a 0, a little loop at the bottom, means partial. A partial negative charge begins to form, and then a partial positive charge forms over here because their nucleuses are getting exposed because their electron has gone too much. So it's getting somewhat of a charge over there. So water has what's called a polar nature. It creates poles. One end of the molecule is negative and one end is positive. So it means that that molecule is polar. Opposite ends have different charges. And it's because of this unequal sharing. Okay? Well, if this electronegativity gets real high, what happens is then they actually pull apart, and the electrons just get pulled right over onto another element like sodium and chlorine, and the one who just takes the electron becomes negative and the other one becomes positive, but their clouds don't overlap. But they do attract because they, like opposite charges, do attract. Here they're attracted just because they are actually touching and overlap. Same thing here, but here we have some of the cloud disappearing over here, and so the electrons are more here. So this part of the electron cloud is darker than these, and their nucleuses are getting exposed. So the positive charge is being felt out in space. Okay? So let's talk about what electronegativity is. Electronegativity is the desire to pull electrons on itself for an atom. And a lot of atoms have a value of electronegativity. And it's not hard to work with. Okay, here's how we do it. Real simple. You got to find the electronegativity values for the actual bonding atoms. So it doesn't matter if there's two of them or one of them or whatever, the bonding atoms. So let's just look at, like, for water, we have hydrogen and oxygen bonding. This is the same bond, we just need to look at one of the bonds. Okay? And basically we want to find whether the values are higher or lower. So we want to compare the values. And how you compare the values is you find a chart. Now there's a chart like this. It's kind of similar to this on page 341 in your book, but you're not going to ever be required to memorize this. I would give this to you on a test. Can you just use these numbers? So like fluorine has an electronegativity of 4.0. Oxygen's 3.5. Hydrogen's 2.1. Beryllium's 1.5. So we just need these. They're very simple little numbers. But what it means is the bigger the number, the more it really wants to pull on an electron, because it would love to be like the noble gas next to it. These have very little pull because they'd probably rather just let you have their electron. But they do pull because there is a charge in its nucleus that will pull the electron in and try to keep it. But they don't pull as strong, so these down here can pull. So actually, we can figure out if something's going to be covalent, polar, or ionic by simply looking at the electronegativity values and subtracting them. So if we subtract them and we get a number between 0 and 0.5, that means it is a covalent bond, one where there's probably going to be a nice perfect overlap. If we get between 0.5 and 2.1, we're most likely going to be polar covalent, which means we'll have overlap, but it will be unequal sharing, and these positive and negative charges will begin to develop on the molecule itself. And if it's higher than 2.1, it most likely will actually just split and become charged. So let's just try this. Will chlorine, if it's bonded to itself, be covalent, polar covalent, or ionic? Simple. We find chlorine. Chlorine is 3.0, and all you got to do is subtract the higher minus the lower by comparing them, or I should say subtract. So we're just going to go with 3.0 minus 3.0, and we get an answer of 0. So 0 means it's going to be right here, it's going to be covalent. It's pretty simple. Let's do it again. Let's do HCl. So our H is bonded to the Cl. Remember, it's always the higher minus the lower when we subtract them. So my Cl is right here. It's 3.0. H is 2.1. So I'm going to put the 3.0 on top minus 2.1, and I get 0.9. That puts me at about a little bit above the 0.5. So this is going to be a covalent bond, but with unequal sharing, and there'll be some polarity in it. So this will be a polar type bond. So it'll still be covalent, but we'll probably start seeing some positive and negative ends on that molecule. Okay? Well, let's look at salt. Salt, chlorine is 3.0, sodium is 0.9. So we take 3.0 minus 0.9, and we get 2.1. 2.1 falls on the line, and you always go to the higher value. So that means it's going to be in the ionic range. So this belongs to that number. That's 0.5 it belongs there. So this would be an ionic bond. If they hook together, then the chlorine is going to pull so hard because it's bigger, it will end up pulling away from the sodium. It'll form an ionic bond, but they'll still stay bonded and attracted, but their clouds will not overlap. So if you want to know, all you would need to know is this little chart right here, this little chart of these numbers, which I will give you. And you need to know these chart, and all you have to do is simply subtract their two numbers and see where they fit into this chart. And you can actually mathematically then calculate from electronegativities which type of bond it's most likely to form. Okay? So scientists actually use this idea too. So thank you for joining me. I appreciate that. And that is the end of our bonding, covalent, ionic, and polar discussion on this unit.